Hello troops, hi everybody. Right, it's time for us to move on. We've already spoken about interference by division of wavefront. That was the Young's double slit experiment. Two slits, interference pattern on the screen. From the interference pattern you can work out the wavelength of the light. That's the experiment that beyond all shadow of a doubt proves that light is a wave. Interference is the test for waves. There's another way that you can produce an interference pattern, though. It's called interference by division of amplitude, and that's what we're going to be talking now about. When light goes from air into a more dense material like glass or water, it reflects back and interferes with itself, and you can get an interference pattern. But before we talk about that, we have to talk about another couple of things. We have to remind ourselves about refraction from higher, and introduce a new idea to you about optical path length. Really, all we've talked about so far, that when a wave travels through space, is it travels a certain distance in a certain time, and you could use speed equals distance over time to work out the speed of the wave. Now we have a problem when we talk about light passing from one substance into another substance. If we have that light that's going from air into a more dense medium, what did we tell you in third year? We told you that that light slows down and bunches up. The wavelength gets shorter and the speed slows down, and then what happens when it exits the glass? It returns to normal again. Slows down when it goes into glass, wavelength gets shorter and speeds up. Wavelength gets longer again on the way out, and there's a couple of problems with that about light decelerating and then accelerating again, and the idea that the speed of light is a constant. So to overcome that, or get around that, or to explain that further, we have to introduce this idea of optical path length. When light travels through air, the refractive index of air is 1. It's almost identical to the refractive index of a vacuum. Right? But when it goes into a more dense medium, that was perspex, or water, or some other transparent material, then it has a refractive index. Refractive index has got symbol N. Remember, it's a ratio. It's the ratio of the speed of light in the air to the speed of light in the glass. Or, in fact, there's the relationship. Refractive index is the ratio of the speed of light in air to the speed of light in glass. Absolute refractive index, by the way, is the ratio of the speed of light in a vacuum to the speed of light in a material. But we can use the approximation speed of light in air, the speed of light in a material. We could also use wavelength in air or wavelength in the material. So refractive index is from higher physics. And when we talk about optical path length, because these waves have been squashed into a smaller distance, and that distance depends on the refractive index of the material, we talk about the optical path length. The optical path length in a transparent medium is the geometric, physical length of the thing, d, but we incorporate the refractive index. Optical path length is the refractive index times the distance that the light travels through. And that relationship is on your relationship sheet. OPL for optical path length. Right? That distance there is sometimes called the geometric path length. So when light travels from air into a more dense transparent material, we need to take the refractive index of the material into consideration when we're looking at the absolute path, the optical path that it travels through. It's the first thing. Okay. Oh, and I should have said that that's measured in meters. Yeah? And that's measured in meters. Because refractive index is just a ratio. It also gets us nicely around this idea of the speed of light changing. Because if you do speed equals the optical path length divided by the time that it takes for the light to move through the medium. You'll get 3 times 10 to the 8 all the time. It's a constant. Okay? Okay, troops. Next thing we're looking for, or looking at, before we get to interference by division of amplitude. This really is interference by division of amplitude, but it's a special case of it. It's called thin film interference. If you've ever seen oil spilled on the road and you see a rainbow, a spectrum of colours in that oil or petrol on the road, it's because of thin film interference. It's because light reflects off the top surface and reflects off the bottom surface of a thin film of some oil, water, glass, some transparent material. So if we've got air here and we've got some other material here, it might be oil, right? And what's going to happen is that light comes in, some of it will be reflected, but some of it passes into the material, it's refracted, so it bends towards a normal if we have a normal there, and it gets reflected off the bottom surface, comes back out and interferes with itself. So although I've separated these two rays out, effectively these two rays would be superimposed on top of each other. So the difference between this path here, the first path, is the light coming in and reflecting off the top surface. The second path is the light being refracted into the oil, coming back and then coming back out again. There is a path difference between those two paths, and that path difference depends on the thickness of the oil. That thickness, let's call it T, right? Measured in meters, right? So if that second ray goes down and back again, then the additional path that it's followed is twice that thickness. Plus, don't forget, that transparent medium will have a refractive index, and it has a refractive index N. So the path difference is going to be 2 times the refractive index times the thickness of the material. That's the path difference that we're going to get between these two rays. Now, will they interfere constructively or destructively? It depends on whether or not that path difference is equal to a whole wavelength or half a wavelength. If we want destructive interference, that path difference has to be half a wavelength. So if that, for destructive interference, then that path difference 2nt will have to be equal to half a wavelength. So that this additional path means that that wave is out of sync with that wave by half a wavelength, so you get destructive interference. If we rearrange this for what the thickness would have to be, then T would be equal to lambda over 4n. Now that relationship is on your relationship. It gives you the minimum thickness that an oil or a coating would have to be, the minimum thickness for destructive interference. The N is the refractive index. Now, as you can see, that thickness depends on the wavelength. So you'll only get destructive interference for one particular wavelength. That's why you see a spectrum or a rainbow in a pattern of oil on the ground. Firstly, the oil isn't always a constant thickness, It depends what angle you're looking at it. And for some colours, you will get destructive interference. For some colours, you'll get constructive interference. And that's why you see a rainbow. Some colours are present, some colours aren't present. So that's in meters. Remember, that's in meters. That's the wavelength. And refractive index has got no units. Sometimes this is deliberately done. You might put a thin film, that's why this is called thin film interference. Sometimes in very expensive camera lenses, they put a thin film, or glasses, spectacles. A thin film is called an anti-reflection coating. Stops any reflections off of your lenses. There's an added complication to this though. We've got air and oil here. Well, it could be air, it could be some other transparent material, it could be water. But here's the added complication. There might be another substance underneath. There might be water. Oil floats on top of water. And that light, right, that light that goes from air into oil, there's another boundary between the oil and the material underneath it. Now we're not going to worry about, because that water can be quite deep, right? This film here is extremely thin. It's only when it's a very thin film that you observe thin film interference. So we're really not going to bother about this, the depth of this material, because it's not going to interfere with our interference pattern. But what it does is it introduces an added complication of what's called phase change. Phase change. Now before we talk about phase change, which you've seen before, that light's coming in. First thing that happens is that light comes in and it hits the boundary between the air and the oil here. Now, the oil has got a higher refractive index than the air. And here's the thing about phase change. When light reflects from a more dense optical medium, and oil's more dense than air is, when it reflects, it undergoes a phase change of half a wavelength, pi radians, 180 degrees. The best way to show you this is on a video using the worm in the corridor. I'll show you that first. Okay, troops. Today we're going to try and demonstrate a phase change on reflection. Right, I'm going to send a wave along to my helper here, my little helper, Mr. McTaggart's going to help me. Mr. Edgar's busy, you see. I'm going to send a wave along and he's going to hold the other end of the wire fixed. Right? Watch what happens to the wave when it's reflected. Eddie, don't you move. Now, you should have seen it comes back on the other side of the wire. I'll do it again. See it came back that side? Yeah. Yeah? This time, I'm going to send the pulse along and Mr. McTaggart is going to move his hand when the peak reaches him to try and match the peak. Watch what happens. Ready? 3, 2, 1, go. Now, you should have seen it came back on the same side. Let's do it again, right? So remember, you're moving your hand out and back to the exact same place. Ready? Right, try and match it exactly.
Can I go first?
Right, you go first. See? See how it's coming back the same side?
Yeah.
So if the end is free to move, the wave comes back on the same side. There's no phase change. Oh, there's no phase change on reflection.
Good one.
If the particle's free to move, we'll do it once more. This time hold yours fixed. Hold it fixed. Ready? This side comes back the other side. Phase change of pi radians on reflection. But this time we're going to move. Comes back the same side. No phase change. You only get a phase change when the wave goes from a less dense to a more dense medium. Mr. McTaggart is a more dense medium.
We can also show you that on the PhET simulation. Now you can do this for yourself. Just Google PHET, PhET, and have a look for this wave simulation. If I send a pulse along this string, then if it's got no end, then that pulse will just keep going forever. But what happens if we have a fixed end? In other words, the particle at the end of the string can't move. Then the wave comes back on the opposite side of the string. And that is what we call a phase change on reflection of pi radians, or half a wavelength. If we send a crest along and it meets a more dense material, or a material with a higher refractive index, then when it reflects, it undergoes a phase change of half a wavelength. It goes along as a crest, comes back as a trough. Now, what about if, instead of that being a fixed point at one end, what happens if we have a loose end? In other words, it's free to move. This is like a wave that's travelling in a higher refractive index material, a more dense optical material, and then it meets a boundary with a lower refractive index material, a less optically dense material. And you'll notice that it comes back on the same side. There's no phase change when you go from a more optically dense material to a less optically dense material, from a higher to a lower refractive index. There's no phase change. So no phase change at that end, but there is a phase change at the left end. No phase change, phase change. Okay, you might need to try that a few times. Have a go at it. You only get a phase change on reflection when you go from a less dense to a more optically dense material.
Right, hopefully you've seen that. So if the light hits a boundary that's more dense, then it gets a phase change of half a wavelength, pi radians. If that light was then to go down here and it hits this boundary, now for example, if that was something like the road, or if that was a solid object, so it was something that was much more dense than the oil was, then that would experience a phase change as well. So phase change there, they both cancel each other out, and you get destructive interference if that optical path difference 2nt is equal to half a wavelength. You get destructive interference. The phase change doesn't bother it, because the same phase change that happens there is happening there. Where it does cause a problem though is if this oil, which is got a higher refractive index than water, say we had, in fact, instead of me using substances, let's put numbers on it. Air's got a refractive index of 1. Let's say we had a substance here that had a refractive index of 1.5, and we had a substance on the bottom that had a refractive index of 1.3. When it goes from air and hits the more dense medium here, we get a phase change at that first substance. But when it gets from here to here, because it's going from a more dense to a less optically dense material, there is no phase change there. Now the added complication then is, if you're only getting a phase change at one of those surfaces, then if the path difference, if the optical path difference is half a wavelength, if you then include the phase change in that as well, you're going to get constructive interference. Because you've got the phase change of half a wavelength plus the path difference of half a wavelength. And both of them combined gets you back to constructive interference again. So you only get that complication though if you have a multi-layered system of materials here. If it was the other way around, if that was 1.3, for example, if it was water that was sitting on top of glass, then you get a phase change there, you get a phase change there, those phase changes cancel each other out, and your optical path difference of half a wavelength gives you destructive interference. Phase change is always going to cause us problems. You have to think about it, right? Let's get back to the notes.
Okay folks, if you wish to take any notes on this part of the work, I suggest you do it with these slides. There's 3 nice little pictures there. There's an oil spill on the road, there's a soap bubble, and there's the surface of a compact disc or a DVD. So, division of amplitude is when light hits a transparent medium, for example glass, and some of the light's reflected from the top surface and some of the light is transmitted through the medium. It's refracted into the material. So that means that the amplitude of the wave is divided. Some of the energy is reflected from the top surface and some of the energy is transmitted into the material. And this division of amplitude can cause an interference pattern as a result of 2 reflections from different surfaces. Now, a spectrum is often seen if petrol or oil is spilled on the ground, and that's because there's reflection from the top and from the bottom surface of the thin film of the oil. And different colours are produced depending on the thickness of the thin film. Some reflected waves interfere constructively and some destructively, and to get a fuller understanding of this, we have to introduce this idea of optical path difference. Now, when light passes from air into glass, it slows down and the wavelength decreases, so the waves punch up. So more wavelengths are squeezed into the same length as shown in that diagram there. And that squeezing in the wavelength depends on the refractive index of the material. An optical path length is defined then as the physical length, the geometric length of the object times the refractive index of the material. So optical path length takes into consideration the length of the material and its refractive index. Now, thin film interference occurs when light reflects from the top and bottom surfaces of a thin film of a substance, for example soap bubble or petrol or oil on a road, and it's because one of the rays reflects from the top surface and the second ray travels a further distance. It reflects from the bottom surface of the film and it travels a greater distance. And the optical path difference between those 2 rays is 2 times the refractive index times the thickness of the film. T is the thickness of the film. And if that optical path difference is equal to half a wavelength, then we get destructive interference. So for that particular wavelength, you will not see any reflected light of that colour or that wavelength. So 2nt equals half a wavelength. If we rearrange that for t, we get t equals lambda over 4n. And that relationship is on your relationship sheet, but note it is for the minimum thickness of a thin film, usually for destructive interference, for anti-reflective coatings, but you have to take care with phase change on reflection. Now, we've been over this when we had a look at the FET simulation. I suggest you go and do that yourself. But basically, when a light wave hits a more dense medium with a higher refractive index, for example when it goes from air to glass, then there is a phase change of pi radians on reflection. When it reflects, it undergoes a phase change of 180 degrees, and that's because the particles in the more optically dense material are more fixed in position. And when light goes from a more optically dense material and it meets a boundary with a less optically dense material, so from higher to lower refractive index, there is no phase change when it reflects. So that takes a wee bit of careful thinking to take into consideration the 2 materials that the reflection is taking place between. Right, I think an example would maybe make this a bit easier. So if we have a soap film on a car windscreen and that soap has got a refractive index of 1.35, the thickness of the film is such that green light with a wavelength of 550 nanometers isn't reflected due to the destructive interference by the soap film. We have to calculate the minimum thickness then of the soap film. That relationship is on your relationship sheet. D equals lambda over 4n. We know what the wavelength is, it's 550 nanometers. If if we divide that by 4 times the refractive index, you get 1.02 times 10 to the minus 7 metres. That would be the minimum thickness that the film would have to be for that wavelength of light not to be reflected. Also take care to notice here that there is a phase change at the first boundary because it goes from air to soap, goes from a lower to a higher refractive index, so there's a phase change, but there's also a phase change when it meets the boundary between the soap and the glass, because again it's going from lower to higher refractive index. The effect of those two phase changes then will cancel each other out, and so the reason we get destructive interference is because the path difference, the optical path difference, is half a wavelength. And that maybe gives us a hint with part B. It says explain why the windscreen has a purple colour. Well, if the green isn't being reflected, then the other colours in the spectrum are being reflected. So the red and the violet ends of the spectrum are reflected most, and they mix together and produce that purple colour that you see. You'll sometimes see people's glasses with an anti-reflection coating. It's a kind of purple colour that you see reflected from them, or from expensive camera lenses. A bit like this. So if it's a soap film or an oil spillage, you see a spectrum. It's a random interference pattern due to irregular thicknesses of the film. But some expensive camera lenses, or you can pay an extra £50 when you buy your glasses, they have a thin coating deliberately placed on them that produces destructive interference for one particular wavelength, usually green because it's in the middle of the visible spectrum. This is called lens blooming. It's an anti-reflective coating, and it's designed to produce maximum transmission of the light through the lens into your eye or into the camera. But there's the relationship on your relationship sheet. The minimum thickness of the coating for one particular wavelength is lambda over 4n. That's it. See you in the next one.